I am going to start today with just some basic background of color perception. I actually created these slides yesterday, and then the voiceover didn't work, so I kind of gave up for my class yesterday, and I'm going to start, but just doing the background and basics, and then doing the vast majority of color perception on Wednesday, Thursday. I have a quote here from an expressionist artist and art teacher, Joseph Albers, who is quoted as saying, "In perception, a color is almost never seen as it really is, as it physically is. There is not another, I think, aspect of perception that makes it quite as clear as color vision that what we are seeing is the psychological interpretation of the environmental world." When we look at the physics of the visual world of color, we are looking at wavelengths, and how we interpret those wavelengths is dependent not just on the cones, how many cones, and all of that, and then what's going on in the cortex and our interpretation of something like that gold white versus black blue dress, where perhaps we have different expectations of the lighting, and we're doing this kind of color constancy, and we're doing that differently than other people individualistically, but also just the context in which that wavelength is being presented. And so you might not be surprised. So Joseph Albers was an expressionist artist, and he was one of those people who looked at a lot of boxes and just geometrical figures. For a long time, I thought these people were, what were they really doing? They're drawing squares. But the more I have learned about Mark Rothko, Joseph Albers, and some of these other expressionist artists and what they were trying to do, you can see what Albers is doing is he is playing with color in a very artistic kind of manner. And I know you're going to believe me when I tell you that the punchline here, if I ask you about the square that's up in the center top versus the square that's down in the center bottom, that those squares, well, if I ask you what do they appear the same, most people would say they do not appear the same. To me, the top one appears kind of orangey, and the bottom one appears kind of browny. But actually what's happening with the wavelength of what's the stimulus, environmental stimulus from the world, that's the same exact wavelength being reflected into our eyes. And the reason they look different is because the interpretation is going to be different depending on the context. And context is just one example of what's influencing our interpretation of color. So again, this is something that's going on in the mind, and this is a psychological experience. Just as all perception is, it's just really, really clear with color vision. I'm going to start out with these questions, and I'm going to end up with these questions, and usually at the end I ask students to answer these questions, and obviously that's not going to happen this time around unless somebody decides right now that within the next, because I probably won't completely finish color vision on Wednesday, Thursday, that you want to go ahead and email me an answer. I will read your answer on the next video or the video after that, because it's much more fun if other people are playing along. But if I ask the question, what does color vision or color perception do for us? What physical attributes of the object influence its perceived color? What physical attributes of an object's environment influence its perceived color? We were just looking at that. We're going to keep talking about that. And how can we describe our color experience? Or how would you describe your experience of color? Whether that is to someone else, if you're just trying to figure out, are we seeing the same thing when we're seeing red? Or to somebody who is maybe blind and has never had an experience of color, how would you describe that experience? And as some of this background, I'm just going to repeat what we actually did at the very beginning, but now since we had that hiatus where we discussed the various different sensory modalities, it's a really good idea to go back to what is the stimulus in vision. It is electromagnetic radiation. If you remember, that is what gives us our light. And we know that it travels as a wave, and that it is made up of particles, of photons. And at this point, when we talk about color vision, we're going to talk about it even more so as a wave, as what is causing our perception of color are aspects of that wave. So the amplitude or the height of the waveform gives us our perception of brightness. So how much light is being shown off of something is one aspect of the brightness of a color. And then the wavelength, the distance between the peaks, gives us our perception of color, or really a better way to say it is hue, because pretty soon I'm going to be talking about chromatic colors versus achromatic colors. And so when we talk about color as the red, orange, yellow, green, blue, indigo, violet, I just did that all. Did I do that in the right direction? Right, you fib. When we're talking about colors, those are really the hues, the chromatic colors. And what's important there is the distance between the peaks. And so the longer that wavelength, the more red, yellow on that end of the spectrum, and the shorter that wavelength, the more blue, indigo, violet we become. And then the purity or the mix of the wavelengths. So this is the perception of saturation, or really the richness of colors, which I'll try to show an example of trying to distinguish between amplitude and purity, which to some extent for me is, I'll start talking about my lack of ability with colors here in a minute, but is hard to really distinguish perceptually for me. So, but I will, as much as I can, try to make that clear. And so here I'm starting with the physics, right, the stimulus, and telling you what that translates to as aspects of our perception. And here we are looking at the electromagnetic spectrum similarly as we did before we started talking about other sensory modalities. In this case, this is flipped around, which is interesting to do, I think, after talking about hearing, because I say a lot of things about our auditory world and the auditory stimulus seem really backwards. And so when I first taught all this, it felt like this really jarring. I didn't like moving into hearing in the auditory world, but I've always been very much into music. And so you can tell my auditory world is really important to me. And I've really appreciated getting to understand some of the physics and so forth, especially in comparison to vision, which is just completely different stimulus, but we talk about them with these similar frequency versus wavelength, where the frequency is really wavelength flipped around because it's how many cycles or how many waves per second. So the lower the frequency, the higher the wavelength. And so now we've flipped our wavelength around. We're looking at the electromagnetic spectrum. And as we stated before about this stimulus of vision, we have a teeny tiny sliver of the electromagnetic spectrum that we get to see. And I think if we had much more of this, we would easily be overwhelmed with information. If we were seeing radio waves and microwaves, then that would be a lot of extra information. And it really feels like kind of enough information to me. And so we have our little sliver from about 400, sometimes estimated at 360, 400 to about 700 nanometers. So again, the nanometers are billionths of a meter, so really unfathomably small are these wavelengths. And as we move into shorter and shorter than 400 nanometers, we get into ultraviolet and then X-rays and then gamma rays. We do have some animals that are seeing the ultraviolet rays. It looks like birds, butterflies, some fish are seeing those ultraviolet wavelengths. As we get longer than 700 nanometers, we start to move into infrared waves, microwave, FM radio, TV, AM radio. And again, we have some animals that are higher than us in the spectrum that are seeing the infrared rays. Some fish, and then snakes as well. And I might put seeing infrared. The snakes, what they do is they are sticking out their tongue, right? And they're actually sensing infrared wavelengths or infrared information. But again, we have our tiny sliver, and we're not seeing the same exact sliver as the other animals around us necessarily. And so again, I'm going to flip things around where now we're talking about our perception. What are the aspects of perception of our color vision, and how do does the physical stimulus translate into our perception? So this is the same exact thing as 2 slides ago, except flipped, talking about this is our perception and this is how we get the perception, just so we're doing this in both directions. The perceived color, and then I'm saying everything I want to say. The perceived color is the dominant wavelength. So as I said, usually I'm drawing this on the board and I'm making those nice sine waves the best that I can. Because when you start drawing the wrinkles in the sine waves, it gets trickier to repeat the wrinkles for somebody who's not really an artist like me and doesn't actually control my hands very well. But so if I'm drawing the dominant wavelength, if I'm drawing the sine waves, remember that we're only seeing those perfect sinusoidal waves when we are looking at sunlight that is being refracted through water or through a prism or something that is creating the rainbow. There are experiments that are conducted where they have created a monochromatic wavelength light, but usually what we're seeing almost always out in the world is some mixture of waveforms. And our perceived color, when we're looking at something that appears to be blue, it's going to have a mix of wavelengths in there, but its dominant wavelength is going to be in that kind of shorter spectrum of about 450 nanometers. Almost, but maybe getting towards 500 nanometers. So the longer wavelengths are red, the shorter wavelengths are violet, but those are really the dominant wavelengths. If we look at perceived brightness, so really this is, you can think of this as how much light is being shown onto something that is red, and so how much light is being reflected versus when you're in a dimmer light, that red is going to appear less and less bright. Okay, and that is the amplitude or the height of the waveform. When I'm drawing it on the board, I usually scribble this a little bit as thicker in the marker, and then say, it's the best I can do for amplitude because I can't just change the lights for just one piece of this. And then perceived saturation is how pure versus how mixed are the wavelengths. And again, we're really not seeing those pure wavelengths very often. Usually they're mixed, and the question is how mixed are they? And I have the example here of pink really being a desaturated red. So if we're looking at those rainbow colors, those are considered to be the saturated colors. And as we're changing those, they're becoming they're becoming desaturated. They're becoming either kind of muddier or with a mixture of wavelengths, or they're getting lighter and lighter, like we're mixing white in with them, like pink is for red. Yep, my picture falls off the screen a little bit, but we can see the last, so that last one over as we're moving from saturation, getting more and more saturated. We're moving from pink to red in the case at the top. And then what should be along the bottom is showing us pretty much brightness. So as we're moving from red, as we're getting into dimmer and dimmer light, as we move down, and then as we're moving down, we're getting less and less bright, but then we can change the saturation of that as well. And this is, I used to not like this picture because, again, brightness and saturation are a little bit confusing to me, but and I'm gonna again keep talking about my lack of really ability with color, but so I hope that helps you all. Okay, and my final slide today is the basics of color vision. Sorry for my Monday Wednesday group. This is the first group of slides in the day, but my final slide for this PowerPoint is the last piece of the basics of color vision, of how we're going to be really using the terms red, yellow, green, and blue to discuss color vision. And really, if we look at any color, we can use those terms and say something's a bit of a reddish yellow or a yellowish red, and we can use those terms to at least get close to the description of pretty much any color. We also have these extra spectral colors, which are brown and purple, which are really examples because those do not appear on the spectrum anywhere. Purple is really mixing red and blue in this kind of subtractive color mixing, as we're going to be talking about. And so it is not cleanly on that electromagnetic spectrum. And brown, similarly, is mixing several of those colors together in subtractive color mixing. So it's really not on the electromagnetic spectrum. And I'm gonna tell a story here on it's the last time I taught this class. One of the young men in the front says something like, well, what's the difference between purple, indigo, and violet? I mean, really, those are all the same, right? And I said, no. Purple is a mix of red and blue, and indigo and violet are on the end of the shorter wavelengths of the spectrum. And if you look at them, they're going to appear different. So that's the scientific explanation of that, which is what I know. If you showed me a purple and you showed me an indigo and you showed me a violet and you didn't show them to me side by side, I might not even be able to tell that they are different from each other. I think I might be able to tell, but mostly I would just say I don't know. I don't know which is purple, which is indigo, and which is violet unless they are labeled by somebody else for me. I am one of those people. If you noticed earlier in the semester that I wear black or khaki pants every day because I don't match my colors well at all. And so, yeah, I gave him that scientific explanation. Purple is a mix of red and blue. Indigo and violet are shorter wavelengths than blue on our electromagnetic spectrum, and you can see them in the rainbow. And as I was talking, the woman next to him kind of just rolls her eyes and looks at him like he's crazy. And she says, obviously there's a difference between purple and indigo and violet. They are different colors. And, so she's having the experience of those colors on a much different level than I am. And so where you are on this is you can kind of right now put yourself into how much better you are with colors than I am, or if you're just more like me, I really don't know. If you put the three side by side, I'm going to say, yep, they appear different. But if you ask me to label them, I might have problems. And if you ask me to match or not match them, to build different purple outfits, I would not be able to do that like a lot of people can. So I'm going to end here today, except for the Monday, Wednesday. This will be the very beginning of the color vision. This is the very beginning of color vision. We're back into higher aspects of vision, and that's always fun. And we will discuss some eReserve articles next Monday, Tuesday. So I'm getting those up right now, right after this.